Thanks, Jessica, and thanks to GeoHugs as well for asking me to give this presentation. I particularly want to thank Saracen Gold Mines, now Northern Star, for funding the project, and also acknowledge the help of some of my colleagues who assisted with this project. The Yilgarn Exploration Targeting Atlases established a statistical association between gold and intrusions of the mafic and cyanitic groups in the eastern goldfields of the Yilgarn Craton. The cyanitic and mafic groups are volumetrically minor components of a much larger Yilgarn granite history dominated by high calcium and low calcium granite groups. This map shows the distribution of cyanite group samples collected by Champion and Cassidy and color-coded according to the supersuites that Cassidy and Champion assigned to them. Notice initially that many of these samples are unassigned, they're the pink ones, but that there is a concentration of cyanitic group intrusions in the Laverton tectonic zone, where gold mines at Wallaby and Jupiter are associated with Wallaby supersuite intrusions. The central Kalgoorlie-Canalpi rift is less densely populated with cyanitic group intrusions, but there is an active gold deposit at Karari-Whirling Dervish, which I'm about to talk about today, associated with a cyanitic group intrusion or intrusions that I believe can be assigned to the Mount Munga supersuite. The western side of the Kalgoorlie-Canalpi rift is depleted, or there aren't many cyanite group intrusions there. In the Kalgoorlie terrain on the western side of the rift, gold is associated with mafic group intrusions, shown in white on the map. Now, the peak emplacement period for cyanitic group intrusions is at 2665 to 2660 million years, and they separate an earlier major pulse of high calcium granite magmatism and a later pulse of low calcium granite magmatism. So this spatial association between gold and cyanitic group intrusions immediately raises the question of what is the nature of any genetic connection between the two. I have already referred to the similarities between some of the cyanide-associated gold deposits in the eastern goldfields with Phanerozoic alkalic porphyry systems, both in terms of the bulk composition of the intrusions themselves, and also the associated high temperature hydrothermal alteration that envelops in these intrusions. In establishing a genetic link between intrusions and gold, geochronology often takes a lead role, and where the age of the intrusion and the age of the gold overlap within error, it is presumed that the mineralisation can be classified as intrusion-related, implying a magmatic hydrothermal or fluid. Suitable minerals for dating are not always present, and in this case, Karari-Whirling Dervish being one of them, an alternative route is required, and the route we have taken in this presentation is to compare the hydrothermal alteration in the mineralisation with the hydrothermal alteration that might be expected to be caused by fluids emanating from the associated intrusion. Here is the story of our geochronological study at Karari-Whirling Dervish. Alkalic magmas can dissolve much zirconium, and it was found impossible to generate a zircon mineral separate from any of the 8 intrusion samples studied. Instead, we have coarse and abundant apatite in every sample. And the decision was made to date these using the uranium-lead method and LAICPMS. The results of this study provided a diverse range of ages with large errors, which hasn't really helped in establishing the age of the mineralization or any connection with the intrusions. Two of the intrusions, KA2 and KA7, nevertheless, give very old dates. The vertical red line on the figure on the left is at 2,675 million years and separates volcanism and early deformation from late deformation and regional metamorphism. Samples KA2 and KA7 are both older than 2675, even with their errors, and this makes them the two oldest cyanitic intrusions in the Yilgarn Craton, extending the currently known range to significantly earlier dates. The more complex apatite grains in KA4 and KA1 yielded younger dates, but it's very difficult to judge both the impact and significance of hydrothermal alteration on these apatite grains. We see here the Karasue Dam camp where Karari-Whirling Dervish gold deposit is located. On the left is an aeromagnetic image with the Karasue Dam basin outlined in black. The Karasue Dam basin is a succession of felspathic volcanoclastic rocks which host 4 or 5 gold deposits with similarities to Karari and Whirling Dervish. The felspathic sedimentary rocks are intruded by alkalic plugs and sills and dikes, which have a slightly magnetic character and can be discerned in the image shown there on the left. In the central panel, this is a map of hydrothermal alteration in the Karasue Dam camp. It's a zoned 20 by 3 kilometre hydrothermally zoned basin with the core of the zoned alteration formed by the alkalic intrusions and their associated potassic and sodic alteration facies. Outboard of this, in yellow, is a muscovite-rich zone, which is formed by strain accumulation during subsequent regional deformation. This is not a phyllic alteration zone, there's no pyrite. And finally, the green facies is a chlorite alteration facies, which probably has some connection to metamorphism and shows an association with the north-south faults. On the right, we have a map of the Karari open pit, which can be divided into 3 domains, separated by faults. In the east, the Eastern Intrusive Complex is a mass of monazite porphyry, syenite porphyry, and lamprified dikes. The central panel is predominantly felsic volcanoclastic rocks intruded by dikes of syenite porphyry and lamprifier. There is no economic gold mineralization in the Eastern Intrusive Complex, which is confined to the central mineralized zone and is associated with bleached, hydrothermally bleached volcanoclastic rocks, which overprint a sea of potassic alteration defined by hydrothermal biotite. This is a gravity image of the Karari-Whirling Dervish area. And the first thing to note is that this north-south Osman fault, shown in white, has displaced the Karari-Whirling Dervish deposit into their current components dextrally by 1 kilometre. Surface rocks in this area are felsic volcanoclastic rocks, and they can't account for the strong gravity signal shown in this image. That gravity signal is attributed to underlying denser greenstones, probably basaltic andesite, which has been identified in the area more recently. Underneath the two open pits, there is a circular gravity low indicating that less dense material has punched through this basaltic andesite, or whatever it is, and suggests the presence of a substantial intrusive complex beneath the mineralisation. In fact, the nature of this unexposed intrusive complex is probably indicated by the Eastern Intrusive Complex, which is anyway believed to underlie the central mineralized zone as a result of reverse movement on the hanging wall fault. Also shown in this image are the drill traces of several diamond holes which have been sampled for this study. Most of the intrusion samples come from the Eastern Intrusive Complex, although there are two from the central mineralized zone. This is what the syenite porphyry intrusions look like. They're packed with alkali feldspar phenocrysts. The ground mass has a sort of darker color because of the presence of hydrothermal biotite. And this hydrothermal biotite forms anastomosing seams which swing around the alkali feldspar phenocrysts. One of the less altered samples in the collection, Ka5, is shown on the lower left, where, as well as alkali feldspar phenocrysts, we can see phenocrysts of amphibole, biotite, and magnetite. Plagioclase phenocrysts are rare to absent in these intrusions. Where we do see plagioclase, it's normally mantled by alkali feldspar, suggesting that these were transolvous magmas that crystallized plagioclase and alkali feldspar together for a short period before entering the hypersolvous field and crystallizing alkali feldspar alone. The colorful images in this slide are TEMA images. Now, TEMA is a form of SEM, or scanning electron microscope analysis, which is carried out pixel by pixel, and the resulting spectra are interpreted in terms of a mineral, which then contributes to a mineral map such as you're seeing here. We're going to see a few of these, so I'll explain the color scheme. K feldspar is pink, albite is cream colored, biotite is green, quartz is orangey brown, and calcite is blue. Immediately apparent is the K feldspar rich nature of the phenocrysts and the albite rich nature of the ground mass. This is seen in a spectacular form in the lower right, the sample Ka4, where the phenocrysts are almost entirely K feldspar and the ground mass is almost entirely albite. There's no magmatic mechanism for doing this, and it really requires a pervasive hydrothermal fluid to facilitate the exchange of alkalis between K feldspar and albite. Notice also in the lower right that zones of biotite alteration are accompanied by an increase in the albite content of the ground mass. TEMA images also indicate the presence of barium-rich K feldspar as relics in the phenocrysts. The barium-rich K feldspar is replaced by barium-poor K feldspar, and in doing so, barium has been released and is trapped as numerous inclusions of barite within the alkali feldspar phenocrysts. Now, in order to achieve this, the hydrothermal fluid that altered the barium-rich K feldspar phenocrysts must have been carrying oxidized sulfur. Here are some microprobe images of this barium-rich K feldspar, showing both barium-rich K feldspar as the brighter component and barium-poor K feldspar as the darker component. The bright inclusions in here are all barite, and the black pits or holes in two of the samples are interpreted as former sites of barite, but that the barite has been dissolved and removed, a consequence of the negative solubility coefficient of barium sulfate. These barium-rich K feldspar domains contain up to about almost 1% barium oxide. Scanning electron microscopy has also identified a barium-rich biotite in one sample only, Ka5, and there it is quite rare. For the most part, the biotite has re-equilibrated with hydrothermal biotite, which has a low barium content. This barium-rich biotite, shown in the backscattered electron image, contains up to almost 3% barium oxide and 2% titanium oxide. Figures are comparable with biotite phenocrysts, magmatic biotite phenocrysts from other alkaline intrusions such as lamprifiers and lamprolites. Also, notice the necklace of magnetite around the margin of the biotite grain on the right. This indicates that the hydrothermal fluid which produced the biotite was at least moderately oxidized. On a standard composition plot, all of the biotite at Karari or in the Karari intrusions plots as phlogopite. The XMG over XFE ratio varies from 1 to 2.5. That's quite elevated and suggests a oxidized hydrothermal fluid causing this potassic alteration. In the graph on the lower left, we can see that there is much overlap between the biotite phenocrysts in red and the fine-grained hydrothermal biotite in blue, suggesting that these magmatic phenocrysts of biotite have re-equilibrated with the hydrothermal fluid. Notice also that for each intrusion sample, the data cluster in a certain part of the diagram. And this provinciality suggests that the potassic alteration took place at low fluid rock ratios. Moving next to the apatite. Apatite is abundant and quite coarse-grained in most of these intrusions. It's quite strongly fractured, and those fractures are infilled with hydrothermal biotite. The cathode luminescent image on the right shows that this interaction with the potassic fluid has modified the margins of the apatite grains. Nevertheless, the cores, which are regarded as magmatic, have a epsilon neodymium value of 3.9 to 4, indicating a mantle source for the syenitic magmas. And they also contain up to about 1% SO3. This is a significant measurement because sulfur substitutes for phosphorus in apatite and can only do so in the strongly oxidized state, S6+. So we're looking here at evidence for an oxidized magma derived from the mantle. We can calculate the sulfur content of the syenitic magma using the equations of Lee et al. At 1360 ppm. More images, backscattered electron images of apatite showing the rims of the grains that have been altered by interaction with the biotite producing hydrothermal fluid. These rims are depleted in sulfur, light rare earths, manganese, strontium, and chlorine. The light rare earths are redeposited as monazite, either in the rims themselves or the surrounding ground mass. The fact that the rims are depleted in sulfur and chlorine means that the biotite alteration fluid was undersaturated with respect to both sulfur and chlorine. Using the compositions of the apatite rims and the fine-grained hydrothermal biotite, we calculate a temperature of 660 degrees centigrade for this potassic alteration, using the equations of Zhu and Stravinsky for the biotite-apatite geothermometer. 660 degrees centigrade seems quite high, but it's not unreasonable in the context of a cyanide magma solidus of 700 degrees centigrade or somewhat more. Amphiboles. These are sodic or alkalic cyanidic magmas, which typically contain sodic amphibole. But in these samples from Karari-Whirling Dervish, only one sighting of sodium amphibole has been seen. And that's shown there on the lower left. It's largely replaced by actinolite, but the original sodic amphibole was an inclusion within a much larger hexagonal biotite phenocryst. The observed amphibole is actinolite in all cases, except for that one. And the actinolite replaces igneous amphiboles, but also forms acicular aggregates that follow the biotite seams, and the actinolite replaces the biotite. And also we've seen actinolite in the form of albite actinolite titanite veins. Actinolite and albite, with which it is in equilibrium, is a common Greensius facies metamorphic assemblage. But at Karari and Whirling Dervish, these assemblages are only locally developed. So rather than interpret the product as regional metamorphism, we attribute that to sodic calcic alteration, which is a common form of alteration in some intrusive complexes and some intrusive related hydrothermal systems. Finally, two other forms of alteration in the intrusions. One is sodic alteration, represented by Ka2, and otherwise not clearly developed in the other samples. In Ka2 is not only the ground mass, but also the phenocrysts, which are largely albitic. Sodic and sodic calcic alteration are closely linked and interpreted in terms of the up temperature flow of external fluids towards the hot intrusive center. This sort of alteration is observed in other intrusion-related systems, including porphyry deposits, and is believed to take place at about 400 to 450 degrees centigrade. K-feldspar alteration is developed in a very minor sense in some of the intrusions, but is nevertheless very important or significant because this K-feldspar pyrite hematite assemblage that we see in the photographs, the backscattered electron images there, is equivalent to the proximal hydrothermal alteration associated with gold in the country rocks around the intrusion. To summarize what we've said so far, despite good retention of igneous textures, the Karari cyanite porphyry intrusions record extensive subsolidus modification in the presence of a pervasive hydrothermal fluid, such that less than 5% of the remaining minerals can be considered magmatic. These include the barium-rich K-feldspar relics, the apatite grains, excluding the compositionally modified rims, rare instances of barium-rich biotite phenocrysts, and the one example of sodic amphibole. The pervasive subsolidus hydrothermal alteration evolved from early exsolution of albite, K-feldspar, and barite from alkali feldspar, followed by hydrothermal alteration, hydrothermal biotite alteration, including the re-equilibration of most of the igneous biotite phenocrysts. Thirdly, and related to influx of external fluids, sodic and sodic-calcic alteration, and most importantly, but restricted in extent, is the potassic alteration. All of these alteration events are considered to have taken place in the range 450 to 660 degrees centigrade. And most of the alteration is related to an oxidized fluid, except for the sodic and sodic-calcic alteration, which is regarded as more reduced. Lower temperature alteration, that is less than 450 degrees, is probably represented by quartz calcite veins, some hydrothermal biotite, and local chloratization. So what does all this hydrothermal alteration mean for the bulk composition of those cyanitic intrusions? In the left-hand diagram, I'm showing not only cyanitic group intrusions, but also mafic group intrusions. The mafic group intrusions represented by the green envelope and the arrow, which indicates evolution from diorite through quartz diorite to granite. The alkalic cyanite group evolution, shown in the pink arrow, however, evolves from cyanite to alkali granite to granite. Striking on this diagram is the fact that the Karari samples and the Wally supersweet samples, both associated with gold mineralisation, plot off trend at lower silica contents. Similarly, on the potassium versus silica diagram, the Wally and Karari samples are amongst the most potassic of all cyanitic group and mafic group samples. Perhaps this is some sort of fertility indicator that could be used in exploration. At the bottom right, the Karari samples plot as alkalic on an Irvine and Berriger diagram, as you would expect. But all of these diagrams concern major elements which are potentially mobile in hydrothermal environments. So it's best to check the results in terms of immobile elements. This is a standard classification plot of Pierce 1996, and it shows all of the cyanitic group samples plotted there, which straddle the boundary between alkaline and subalkaline compositions. Karari intrusions in particular consistently plot as subalkaline, which is difficult to reconcile with the low modal quartz, dominant alkali feldspar phenocrysts, and the presence of relic sodic amphibole and barium feldspar, amongst other things. My explanation for this is that the immobile elements have actually been mobile, which is not unheard of in alkalic hydrothermal systems. For example, cyanitic group intrusions in the Eastern Goldfields province typically contain titanite as the main titanium phase. Titanite can contain up to several percent, Nb2O5. But in the Karari intrusions, titanite is no longer present. It's been replaced by rutile. Our microprobe measurements of this rutile contain less than 0.1% Nb2O5. So it seems quite likely that significant amounts of niobium have been mobilized out of these rocks during hydrothermal alteration. And this is our explanation for why the samples plot in the subalkaline field. We know also that titanium has been mobile in this environment because in the mineralized country rocks surrounding the intrusions, we find titanite as a key component of hydrothermal stringers. Moving next onto the volcanoclastic sedimentary rocks, which form the country rock to the intrusions. These metasedimentary rocks contain crystals of alkali feldspar, and in some cases, lithic clasts comprising quartz pore, porphyritic volcanic rocks. This evidence suggests that the sediments were derived from a hinterland dominated by alkalic rocks, similar to those which intrude the sediments. All of this requires a very dynamic tectonic environment, probably extensional, in order to account for that complex relationship. The biotite in the volcanoclastic rocks is the earliest hydrothermal event recognized. The biotite looks and has a similar habit to the hydrothermal biotite in the intrusions, and is similarly accompanied by an increase in the albite content of the rock. As well as being similar in appearance, the hydrothermal biotite in the volcanoclastic rocks has a similar composition to the hydrothermal biotite in the intrusions. That's illustrated in the XY diagram there, where the intrusion-hosted biotite in red and blue can be compared with the hydrothermal biotite in the volcanoclastic rocks, which are shown in black. They have similar magnesium-iron ratios. They also have similar titanium contents and silicon-aluminium ratios. The only difference between hydrothermal biotite in the intrusions and the volcanoclastic rocks is that the latter contain more fluorine and less water. Well, the FOH ratio is considerably higher, suggesting that the hydrothermal fluid responsible for biotite alteration in the volcanoclastic rocks was more saline or less hydrous than that in the intrusions. We can calculate the fugacity ratios of the halogens to water in the hydrothermal fluid that produced this potassic alteration using the equations of Munoz. And this shows that the biotite, both in the intrusions and the volcanoclastics, plot in a chlorine-rich water poor part of the triangle. And zooming in on that little triangle, we can see that the biotite in the intrusions is more water-rich, less chlorine-rich than the biotite in the volcanoclastic rocks. These, the biotite in the volcanoclastic rocks indicates a hydrothermal fluid with more fluorine and chlorine compared to water than is found in the intrusion-hosted biotite. These calculations are carried out at 650 degrees centigrade based on the apatite biotite geothermometer. But if we modify the temperature to, say, 450 degrees centigrade, the fluid responsible for biotite alteration in both the volcanoclastics and the intrusions just becomes a little bit saltier. But the biotite alteration is not mineralized. The gold mineralization at Karari-Whirling Dervish is hosted in these sorts of hydrothermally bleached rocks. They're fine-grained, dense aggregates of feldspar and carbonate. The carbonate in this instance is dolomite, ferroandolomite, in contrast to the calcite, which is dominant in the intrusions. The hydrothermal bleaching postdates potassic alteration as indicated by the xenoliths of or remnants of potassic alteration in that photo shown on the left. These rocks contain extensive fine-grained disseminated pyrite, and they're extensively fractured and cut by multiple generations of carbonate, quartz carbonate, and biotite veinlets and stringers. Amongst the more important of these are the biotite stringers, shown in black in the top photograph, and cherty grey quartz pyrite veins shown in the lower photograph. We'll look at these more carefully in a little while. Studying the nature and genesis of these bleached hydrothermal lodes is quite difficult petrographically because the alkali feldspar phenocrysts are poorly twinned and the ground mass is very, very fine grained. Even with the assistance of TEMA, some hydrothermally bleached lodes, such as the hanging wall lode, located in the hanging wall fault, are difficult to unravel and decipher. That sample there, Ka25, from the hanging wall lode, is predominantly banded quartz and K feldspar, the blue being an asymmetrically folded calcite vein. So ductile deformation in the hanging wall lode has really obscured the initial formation of the composite hydrothermal unit. The other lodes, however, are more associated with brittle deformation, and here we can begin to get some insights into the formation of these hydrothermally bleached lodes. For example, in the bottom right there, WD9, we can see that some domains are relatively K feldspar rich, pink, while others are more albite rich in cream. Use of the scanning electron microscope and TEMA imagery show that albite and quartz appear as relics in a replacive sea of K feldspar, the K feldspar in that SEM image being the paler grey. In fact, it's very difficult to isolate a sizable domain of that sodic alteration represented by the albite, but there is one shown here where the sodic alteration assemblage is considered to be albite, ferroandolomite, and rutile. This is overprinted by biotite stringers in the image on the left, and there's also some rank igneous apatite in there. But the albite dolomite rutile assemblage contains no Fe3+ bearing minerals, and so this is interpreted as a relatively reduced hydrothermal stage or relatively reduced hydrothermal fluid. And the sodic alteration is correlated with sodic and sodic calcic alteration in the intrusions. This is what the hydrothermal K feldspar looks like in the composite hydrothermally bleached lodes. Generally speaking, it's a sea of replacive K feldspar, and where we can zoom in on that K feldspar, we can see that the pyrite is more closely associated with K feldspar than the relic quartz and albite domains. We've even seen examples of K feldspar pyrite veinlets that cut across the hydrothermally bleached matrix. The presence of columnar, is that the right word? Columnar biotite and K feldspar in the pressure shadows of coarse-grained pyrite suggests that this was a high temperature mineralizing event. And LA-ICP-MS analyses of this sort of disseminated pyrite typically returns values of 0.1 to 1 ppm of gold, and with few metallic inclusions detected. The photo on the SEM image on the bottom right shows a replacive zone of K feldspar associated with hematite and pyrite, indicating that this was an oxidizing hydrothermal event. The hematite is replaced progressively by rutile as the contact with reduced wall rocks is approached. Here we are looking again at that cherty grey quartz pyrite vein. And notice how it has a thin, pale selvage, which postdates alternating bands of biotite alteration and hydrothermal bleaching. The team image on the right shows the selvage on this vein is formed mainly by K feldspar, pink, and dolomite or anchorite in blue. Locally, these rims or selvages are very pyrite rich, and where we see pyrite there, we also see microscopically numerous inclusions of native gold. LA-ICP-MS analyses of this sort of pyrite ranges from 1 ppm up to 34 ppm gold. So this is high-grade material. The LA-ICP-MS analyses also identified many metallic inclusions in the system: gold, silver, tellurium, lead, and bismuth. The final act of the gold event is represented by these biotite-pyrite-rutile stringers, some of which contain chalcopyrite and magnetite as well. Close examination of the pyrite from these stringers indicate that it contains inclusions of gold, chalcopyrite, and rutile. And the XY plot on the lower left shows the composition of this stringer biotite in orange. Notice that it extends to very high magnesium ion and fluorine hydroxyl ratios. This could be taken to indicate, again, an oxidized hydrothermal fluid, but we need to be cognizant of the fact that this biotite is closely associated with pyrite, and that the sulfides may be competing for iron with the biotite. Nevertheless, we have independent evidence that this was an oxidized fluid. The stringer rutile contains high abundances of both tungsten and vanadium, which are well correlated. And the slope of that correlation, or the slope of the correlation between trivalent ions and pentavalent ions, is greater than 2, indicating, based on the studies of Scott et al., that this was a strongly oxidized fluid. The temperature is less well constrained. On the lower left there, I'm showing a plot which plots titanium against magnesium over magnesium plus iron. And this is the titanium in biotite geothermometer. The compositions of the biotite suggest temperatures of about 500 degrees centigrade. However, the experimental conditions for this titanium in biotite geothermometer at 4 to 6 kilobars is inappropriate for the Karari-Whirling Dervish gold mineralisation, which likely formed much shallower depths and pressures equivalent to 0.5 to 1.5 kilobars. The temperature of biotite formation increases with decreasing pressure. So the 500 degrees centigrade measurement for the Karari volcanoclastic hosted hydrothermal biotite would have formed at a minimum of 500 degrees centigrade based on this plot. We can also see that the average of all the intrusion hosted biotite is very close to the composition of the stringer biotite, and that intrusion biotite is calculated or estimated to have formed at 660 degrees centigrade. So perhaps the stringer biotite wasn't forming under conditions that were all that cooler. The sulfur isotopes. The sulfur isotopes show that the delta S34 of pyrite is almost entirely negative, which is consistent with a strongly oxidized hydrothermal ore fluid. The samples from Ka20, which is that cherty grey quartz pyrite vein are shown here in purple, and they cluster around a value of -9 to -10, consistent with the idea that this pyrite was formed by some disequilibrium process, such as phase separation or flashing. On the other hand, the run-of-the-mill pyrite, extending from 0 to -6 per mil, probably formed by a redox reaction in which an oxidized ore fluid came into contact with reduced sodic altered wall rocks. Also notable in this diagram is the complete absence of mass-independent fractionated sulfur. All the sulfur in pyrite is plotting in the MDF field. Now, this is perfectly comfortable or consistent with the ore fluid having been derived from a magma derived from the mantle, as, for example, the associated cyanitic intrusions represent. But also indicates minimal input from crustal sources of sulfur or near surface fluids. There are other deposits in the eastern goldfields which have extensive negative delta S34 values. One example is the oxidized phimoston lodes, which nevertheless extend into positive delta S34 territory. Another is Bellerophon in the St. Ives camp, where delta S34 values do not extend to values lower than -6. Just to summarize the hydrothermal history in the intrusions and the volcanoclastic rocks and make some correlations between them, I present this diagram. The early hydrothermal biotite alteration seen in intrusions and volcanoclastic rocks can be correlated, as well as can be the sodic and sodic calcic alteration in both environments. And we have evidence from the intrusions that, at least in a small volume sense, the potassic K feldspar alteration responsible for gold in the country rock has also been present in the intrusions. In terms of porphyry systems or intrusion-related systems in general, this diagram from Dick Tosdell and Don Dillies shows, in terms by the red envelope, that hydrothermal proximal alteration associated with gold at Karari-Whirling Dervish, dominated by biotite and K feldspar, formed at low pressures and high temperatures, 5 to 650 degrees centigrade, that sort of range. So here is the model for Karari-Whirling Dervish. It begins with extraction of small volume melts from a metasomatized mantle source, transported into the upper crust via crustal scale faults and leading to the construction of an alkalic magma chamber in the upper crust. Syenite porphyry dikes emanate from the roof of this magma chamber, and the alkalic intrusive center is capped by a carapace of biotite alteration. The next stage is the influx of external fluids, causing sodic calcic and sodic alteration in the carapace and the syenite porphyry dikes. This was a very important stage because it changed the rheology of the roof rocks from very weak biotite altered sediments to rheologically strong hydrothermally bleached rocks. They were therefore prepared for fracture during subsequent deformation and stress, firstly forming an almost pervasive crackle breccia network in which K feldspar, pyrite and hematite replaced the reduced sodic assemblage. This was the low-grade gold event, and probably volumetrically the most important source of gold in the deposit. However, it was superseded by more fundamental fracturing, which led to the formation of cherty grey quartz pyrite veins with their enriched selvages and the biotite-pyrite-RUTILE stringers, both of which introduced high-grade gold into the deposit. There's a schematic diagram or cartoon of the model for Karari-Whirling Dervish, in which the present erosional level in the eastern intrusive complex and the central mineralized zone is shown by the dotted black line. I see the following features as consistent with an alkalic porphyry model. Well, first of all, there's the cyanide magma association. Secondly, indications of sodic and sodic calcic alteration. Finally, and importantly, high temperature oxidized hydrothermal K feldspar and biotite associated with gold. The predominance of disseminated stringer and veinlet pyrite, and only a minor role for orogenic type quartz veins. The poor development of sericitic or phyllic alteration in the deposit. And finally, the pyrite, which has a gold, silver, lead, tellurium association and a low arsenic content. There are other features which are not consistent with the alkalic porphyry model, and chief among these is the absence of a broad carapace of stockwork mineralization. The gold at Karari-Whirling Dervish shows quite a strong structural control, which is based on the embrittlement of the syenite porphyry dikes and immediate country rock. There are also features which are inconsistent with the distal source orogenic model. These are the high temperature alteration of the gold-related, these are the high temperature of the gold-related hydrothermal alteration in a greenschist facies setting, and the oxidized alkaline nature of the ore fluid. So to conclude, the geological approach has failed to constrain the genetic ore model at Karari-Whirling Dervish. Alternative approaches are required. The early high temperature oxidized magmatic hydrothermal fluid produced by the syenitic magmas caused hydrothermal biotite alteration in the intrusions and the volcanoclastic country rocks. Structurally controlled ingress of reduced external fluids generated local sodic and sodic calcic metasomatism in both the intrusions and the volcanoclastic country rock, leading importantly to embrittlement of the earlier biotite-dominated altered rocks. Gold mineralization is restricted to zones of bleaching comprising sodic alteration, but related to overprinting high temperature alkaline oxidized fluid results. These include disseminated pyrite in domains of K feldspar pyrite plus or minus hematite, which generated the bulk of the gold in low-grade form. Secondly, first of all, the first classification of gold was probably deposited as a result of redox reactions between the oxidized ore fluid and the reduced sodic alteration assemblage. Secondly, cherty quartz veinlets with associated pyrite and K feldspar produced high-grade gold as a result of phase separation, producing pyrite with numerous metallic inclusions, including native gold. And finally, biotite-pyrite-RUTILE stringers, which also produced high-grade gold. In conclusion, the Karari-Whirling Dervish gold deposit is best classified as an Archean alkalic intrusion-related gold system. Thank you.